Okay, we are starting section 4.5, integration by substitution. The integration by substitution rule is essentially the opposite of the chain rule. So when chain rule was for differentiation, the integration by substitution rule is for integrals. So we have g, a function whose range is in the interval I, and let function f that is continuous on I. If g is differentiable on its domain and f is the antiderivative, then to take the integral of a composition of functions times the derivative of g, as you can see that looks very similar to the chain rule, then all you have to do is take the derivative of the outside and then plus c. So in other terms, if we have u as our inner function, g of x, then to take the integral of f of u, then we just take the integral of the outside function. So we need to recognize this pattern. So we need to figure out what our inside function is, g of x. G of x in this would be x squared plus 1, and g prime is 2x. So when we look back up at the rule, when we're talking about f g of x and g prime, we can see that we have f of g of x right here, our f being that we have g squared, and g prime is 2x. So when we look at the rule, it's telling us all we have to do is take the integral of f, which is the outer function. Our outer function is that we have squared. So taking the integral of a squared, we have the integral of a squared is a cube. So to take the integral, we leave the inner function alone, g, raise the exponent, plus c. Okay, sometimes it's really hard to see this, and there's going to be another process along the way in this section that will make it a little bit easier. Our inner function this time is 5x. So g prime is 5. So we do match the pattern. So when we take the integral of just the outer function, our outer function is cosine, and the integral of cosine is sine. We leave the inside alone, plus c. Anytime that you have any doubts about whether your answer is correct, you can take the derivative of it and see if you get back to the original function, and in this case you would. Okay. So before we do this one, I'm actually going to go down and explain to you what change of variables is, because I think that it's going to be easier just in general to learn this first. So again, if we have a composition of functions times the derivative of the inside, what you do is take the integral of u du, which is f of u plus c. So the change of variables, what you do is figure out what your inner function is. In this case, our inner function is 2x plus 1, so that would be our u. Then we take the derivative of that, and it would be 2, oops, I'm sorry, our x squared plus 1, not 2x plus 1. Makes a big difference. Our derivative would be 2x dx. Now remember, we want that to match what I just underlined, x dx. It does not currently match that, so the way we get it to match is to divide both sides by 2. X dx. Okay, so now that that matches, we put the du back in and take the integral of the function in terms of u. So that du over 2 turns into 1/2 on the outside of the integral, and then we have u squared du. Take the integral of u squared, and it's u cubed over 3 plus c, which is 1/6 u cubed plus c, or 1/6 times x squared plus 1 cubed plus c. That would be our final answer. We have to put that original function back in, the one that we called u earlier. Put it back in for u. We always have to change it back to whatever variable we started with. Okay, so in this function, our inside is u equals 2x minus 1. du is 2 dx. Now look that we don't have a 2, so we need to divide both sides by 2. Now that we match, we put the 1/2 on the outside. Integral of u to the 1/2 du. Integral is u to the 3/2 divided by 3/2. plus c, which is 1/3. We're going to put the u back in, 2x minus 1, to 3/2 plus c. Okay, here's another example. In this example, we figure out what our inner function is. It's u is 2x minus 1. But this one is a little bit different because we take the derivative of u, which is 2 dx, and not only do we not have a 2 in our original, but there's an extra x then left over. So when we plug everything back in, there would be that x on the outside. So whenever there's an extra x, we need to solve for the x in our u that we called. So u plus 1 equals 2x. U plus 1 divided by 2 equals x. We have to plug this in for x when we plug back in the du. So let's continue with the du as well. We have to divide both sides by 2 because we don't match. Okay, so we're going to have that 1/2 on the outside. And then we also have to multiply by u plus 1 over 2 where the x is, times u to the 1/2 du. So we can take the integral of this, but we do have to do some manipulating first. We're going to pull that other 1/2 out, so it's going to be, I'm going to go this way, 1/4 integral of u plus 1 times u to the 1/2 du. We need to multiply in that u to the 1/2, 1/4 u to the 3/2 plus u to the 1/2 du. Take the integral of both terms. 1/4 u to the 5/2 divided by 5/2 plus u 1/4 times u to the 3/2 divided by 3/2 plus c. Plug everything back in and simplify. This turns into 1/10 2x minus 1 to the 5/2 plus 1/6 2x minus 1 to the 3/2 plus c. Okay, here we have to identify the inner function. Remember that when we have sine squared of 3x, that means that our inner function is sine 3x. The whole thing is being squared. You can rewrite it as this and it will help us a little bit. So u is going to be sine 3x. Du is cosine 3x times 3 dx. We have an extra 3, so we need to divide. Now our du matches. So we bring that 1/3 out the front of the integral. We have u squared du. Take the integral of that. 1/3 u cubed over 3 plus c. 1/9 times sine 3x cubed plus c. Okay, so this is just going to tell you how to make the u substitutions, and we have been doing that. You're not always going to have to figure out what the u is. Some of you are going to be able to identify that without going through the u substitution. Some of them are going to be pretty basic, but whenever you need to divide by something or solve for x like we did in the last couple, you will need to show your work. Okay, so there's all the rules again. So let's do this one. Our inner function is 3x minus 1. Du is 3 dx, which means we match. So this is the integral of u to the 4th du. Take the integral. 1/5 u to the 5th plus c. We got to put that u back in. 3x minus 1/5 plus c. This next one you could just go ahead and multiply through to do it, but let's do some u substitution practice. Our u is x squared plus x. Du is 2x plus 1 dx, which means we match. Integral of u du, because it wasn't raised to any power or anything. Integral of u is 1/2 u squared plus c. And then we're going to put the u back in. 1/2 x squared plus x squared plus c. Our inner function is the one underneath our square root, which is x cubed minus 2. du is 3x squared dx. We match perfectly. So now we have the integral of u to the 1/2 dx. Integral of u to the 1/2 is u to the 3/2 divided by 3/2 plus c, or 2/3 times x cubed minus 2 to the 3/2 plus c. Letter D, our u is the function being raised to the squared, 1 minus 2x squared. du is negative 4x dx, and we match. So our integral of u to the negative second, du, since it was on the bottom, integral of that is u to the negative 1 over negative 1 plus c. Plug the u back in. Negative 1 over 1 minus 2x squared plus c. Letter E, our u is cosine. du is negative sine x dx. We need to move the negative over. So we have matchers. Now we have negative integral of u squared du. Integral of u squared is u cubed over 3 plus c. Negative cosine cubed x over 3 plus c. Now we have definite integrals. So far we've only had the plus c's on the end. This one is if we have limits, and what you need to do is figure out what our new limits are. So I think it's going to be easiest to go right into a question to figure out what the new limits are going to be. You're going to go through the process exactly the same when you start. You're going to pick your u, x squared plus 1. du is 2x dx. We don't have a 2, so we need to divide. We match perfectly. Before we put everything back in, what we need to do is take our old limits, so 0. We're going to plug it in to x, figure out what it's going to be now. That changes into a 1. 1 changes into a 2. So now we can plug it back in. We have that 1/2 on the outside, and we have u cubed du. 1/2 times u to the 4th over 4, evaluated from 1 to 2. Now when we change the limits like we just did, we don't have to change the u back into the x terms. If you don't want to change the variables or change the limits, you would have to change it back to x's. This is 1/8 u to the 4th from 1 to 2. When you evaluate that, you get 15/8, which is 1 7/8. I do think that it's going to be easier for you to leave it in the u terms. So changing the limits into the u's is actually going to be easier than changing the whole integral back into x's. Okay, we have one more. Our u is 2x minus 1. du is 2 dx. So this one we need to get rid of the 2, but also we have an extra x. So we need to solve this for x, which is u plus 1 over 2, which we're going to have to plug in, as well as the 1/2. We also need to change the limits. The 1 is going to turn into a 1, and the 5 is going to turn into a 3. Then we have the 1/2 times u plus 1 over 2, that was the x that we're changing, and then it's u to the negative 1/2 dx. First thing you need to do is bring that 1/2 out, 1/4. And what we're going to do, should be a u over here. What we need to do is distribute in the u to the 1/2, negative 1/2, 1/4, u to the 1/2 plus u to the negative 1/2 du. Take the integral, each term. Evaluating the whole thing from 1 to 3. When we do that, save a little time, that's 5 1/3, 16/3. Okay, that was changing variables, section 4.5.